Just very happy to have you. So thank you, Boker Tov. I'm very happy to be here today. Thank you, Uri Amir, that I don't think is here because he's traveling, that is hosting me in Bal that organized the talk, and everyone for being here. Today I'll talk about towards causal AI, and I'm very happy to be here. I should repeat here, it's a pleasure, beautiful campus, and having a good time in Tel Aviv. The topic of the talk is I want to talk about what I believe is a structural gap about how we are constructing AI systems. And I will try, in the general theme, I'll try to diagnose what is this gap and try to argue that causality can help to address it. Everything that I'm talking here today is in my book. It's Causal AI Roadmap for Building Causal Intelligent Systems. There is a draft of the book here that you can download. It's I would say the first kind of modern textbook on causal AI. It should be out, if everything goes well, towards the end of the year in print, to be able to buy a copy. Printed copy is from MIT Press. And I kind of located in the book is a work of many years, and many people in reality, not only my work, really other people is represented in the book. Now, why we're here today? We're here today is like there are some kind of recent breakthroughs in AI that makes everyone very excited. In particular, systems are able to perform extremely well, making predictions in high-dimensional settings. In particular, there's huge progress in the fields, I would say, kind of congratulations in the main field of natural language, right? NLP, some kind of breakthroughs or interesting stuff going on in computer vision, and also reinforcement learning, RL is kind of helping with that. It's kind of fueling some of the excitement. And applications are everywhere. I would assume that many people here is computer scientists, data scientists, statisticians, more in the kind of formal methodological side. Don't need to tell you. All other, I think, buildings in the universities are trying to talk probably with you guys and trying to apply also some of these methods. It goes from medicine to business, agriculture to space exploration, and everywhere in reality. And it's quite amazing. I think so. Like I would say, we're blessed that we are living the time that's so exciting and something like that happened. That's good. But the question that we ask in the lab, kind of reasonable question for an academic, a professor, is a researcher, is about, does this mean that we are done? And what I mean by done here is if you stack more kind of buildings, you go to the around the Israel, I was passing there, and you stack another building for AI engineers, put more quote unquote muscle in the room. Does it mean that eventually we'll get there and maybe reach AGI? It's a matter of just kind of more execution. And that's it. We don't need, there's nothing fundamental missing. And the Gedanken experiment here, thought experiment, is like assuming that we have infinite amount of compute and data. We understand that this is not the case, but even if you assume that this is the case, does this mean that we are done? Because if the answer is no, under this assumption, of course, things will get more complicated if you don't have infinite amount of compute and data. And if not, what is missing? Now I'll go to the other side of there is a breakthrough in the excitement, and I would like to elaborate on what is missing. This is the other side of the coin. That is, those are the current challenges in AI. I would say there are still serious foundational issues. I have been saying that for a few years. I'm glad that some of the leaders of the field that led to the breakthroughs for the era that we're today are starting to recognize that. This is just a quote from Elias, one of the founders of OpenAI, saying that just scaling is not enough. We need new ideas for the next jump. Of course, I'm very glad that people like him is saying something like that. I argue that new ideas not in the open, but again, as I mentioned in the beginning, we have a way of a place to start unraveling from there. And we're not in the square zero trying to do pure exploration here. But then, in any case, I digress. Good conversation for the cocktail party. Jan LeCun himself saying that scaling along will not get to systems that understand the world. Very good. Keyword here is understand. And now digress here. My opinions about the current undertaking of him and the discussion of world models for the moment, at least. I'll take as a positive here signal. This is Yoshua Bengio, someone that I know well, saying that robust and safe AI requires causal understanding. I guess we can be friends. Without it, systems will fail unpredictably. The key word here is unpredictable. We know that systems, we're computer scientists, systems will be failing all the time. The question is about, do we have any type of control over it? And he's claiming that it's not, and of course I agree with that. Now, then let me elaborate a little bit more about what this means that is kind of very high level. And this is starting zooming in about what are the potentially current challenges. I would say that these systems have very low understanding, causal understanding, and they lack the explainability capability. They are, given the lack of understanding, they are unable to articulate explanations first about themselves, and I will defend this point, but first about themselves and also about the world. Very different types of explanations. Because whatever, the AI can't need to explain about why they are doing something wrong. This is related to their model or their reality, and also maybe AI should be explained about the outside, something that is outside the mind, the outside world. But in any case, they are also very prone to unfair and unethical, I emphasize unethical here, decision making. I usually say that this is a punch in the face when I'm teaching, putting the hat, and very excited to teach. I don't teach for a few years the kind of basic ML class that's kind of huge now with hundreds of people. I say a punch in the face, because when we're teaching this class, we say that give me more data and eventually things will be fine. Now, observations, maybe not surprising for the folks in the room, this data is nothing more than a picture of the reality or sample of the reality that we are sampling from. A picture of the reality that we are sampling from. This is data. Now, data, number one. Now, number two, reality is messed up. It's skewed, it's broken, there are many problems in reality. Don't need a PhD in AI or computer science to realize that if you train the AI with this data that is kind of broken or skewed or have these problems, what the AI will do, how the AI in principle could fix that or solve any problem. Of course, more data of this type will not be enough to solve the problem. Then it's, but if data is not the solution, then what's the solution? Then we are kind of baseless here, or we are kind of shaky, given this axiom that we have been teaching our students. I think is a disservice. Maybe I did it many years ago to say that give me more data and eventually we'll be fine. To be elaborated, but in any case, unfair and unethical decision making. They are very data inefficient. You need sometimes billions of data points of millions of data points to learn something that maybe an infant or us would take a few dozen or very few, which kind of shows that there is some kind of tension in terms of what are the representation that we are using, and some kind of mismatch, fundamental mismatch that's related to the understanding at the end. It shouldn't be so hard, some tasks. They are very poorly generalizable, right? And lack robustness. I would say you kind of change the AI for different environments and you can make it break very easily, which is not a proper of the humans. I've never been in this conference room. I've been in others. I can operate relatively okay here using, I will argue, some kind of the invariances of the causal mechanism between the other meeting rooms that I'm being, conference room that I've been in this conference room, even without, almost in an automatic way, which is AI doesn't have that at the moment. It's due to the brute force in a way, and the representation problems. Now, last one here for now, lack of controllability. We have this kind of latent space with billions of parameters, and it's very hard to go there surgically, change these few bits and make they steer the AI or make the AI to move to a certain direction. Things are kind of correlated and quite messy inside the space. Then I'll show even an example, I believe, that we change kind of one bit and then the AI is moving to their own direction. Now, those are very thorny and long-standing problems in reality. Some of them, most of them, in other words, not new, given the scale and the success, a victim of their own success, given the scale in which this technology is deployed nowadays, anyhow, the stakes are quite high, and you should try to solve and be more serious about them. Now, question that we ask in the lab, I ask myself at night, I guess, is do these problems have anything in common? Is Elias just giving a bag of problems that are disparate, or is that kind of underlying theme? And this is my hypothesis. It is Bareinboim, my hypothesis. At the core of these challenges is the absence of a robust causal understanding. The cause, pun intended here, the cause of these issues is about there is very little causality or understanding there. We are doing this, the key observation there, that we're doing this data mining of the correlations at scale, which is buying tons of mileage and a kind of this very cool behavior that the systems have, cool in a sense, but have all this kind of problem. Then it comes in the package in a way. Now, question that follows from that, I think this reason is like, how can we build AI systems that are more trustworthy? And I would say the approach here, like to try to have a more scientific approach to AI instead of being purely empirical. That is the kind of winning side that have at the moment and have the benefits, but can you try to play science in the university and you're a scientist? And here's an idea. Let's model, why not to model the agent environment relationship to a causal language? Let me elaborate what this could be. Because very, very general words. Have the real world on a side and the agent on the other side. This supposedly two entities that are separate. And we have this kind of relationship between them. And I'll quote Turing, and yeah, that says that what we want is a machine that can learn from experience. This is the first paper starting kind of the field of AI. And Turing was right, as almost always, he's the hero here in the computer science. I see quote in the first floor of this building of Turing. But this is kind of great, insightful, underspecified. And why is it underspecified? Because the word experience is too broad. And what I argue that there is different types of experiences. In other words, it's heterogeneous in a way that makes things complicated. Then this is my unpacking here about what experience could mean. I like to modulate or to separate in a way that one type of experience is when the agent is passively, they get the hands, put the hands in the back, and just through perception, through the eyes, or I guess can be the ears, we are kind of, let's say for the eyes, we're seeing this reality unfold. This is one modality about how we experience the world. A second modality is to intervene in the world. Sometimes you go there in this reality, there's a reality running, you join the reality, and you start tinkering and changing things to try to understand which kind of change can you bring about, well, how you are affecting this world. And the third one, is very active, this too. In some, this is active. This is also collecting data from the world. And this is inside the head, inside the box, cognitive box, that maybe we are also interacting with the world, running our own simulations of the world inside the box. It has huge value for the human. It seems that you can do far-fetched simulation, all kinds. Good for art, creativity, and so on, and good to design different versions of the world that do not exist yet. Very related to my previous point about reality is messed up. We need a language that allows us to express different versions of the factual world, of this world, and make the AI to move in this direction. Then which language allows us to do that? We cannot just be fitting the data. But in any case, it turns out that we can formalize in reality different probability distributions or these different types of experience under the name of something that we gave the name even, but it's called the pro-causal hierarchy. Due to you, the pro. Then the summary here is like not all experiences create a PCH, I'll call pro-causal hierarchy. PCH just is too convoluted, but PCH is easy. Not all experiences created equal. Summary of what I said so far, I guess. Now, the recommendation of the PCH or the ladder of causation, my second book recommendation of the 2 out of 2, if you haven't heard or read, recommended, is a general dissemination. I think you probably want more math, but at least if you want to get excited, the book I think is good. It's a first reading on causality in terms of the motivation.
Translated to Hebrew.
Yeah, the book of Lama, of Mahalama, right? The Sefer by Lama. And I don't know why I introduced. I forgot to ask you that because I learned that there is this new word now, the Ma, which is not the original text. It's just the Lama. And I don't know why they did that. Because the causality is not clear to me.
I think it's because of the animal.
The animal?
It's because of the animal. It would only be Sefer Lama.
Oh, it is a bit. We appreciate it. תודה רבה. The observation here from the previous slide about we would like to model this environment, the agent environment relationship. Now, under any environment, I say that there is a causal model that is nothing more than a collection of causal mechanisms. Once this mechanism, which is very weak statement, it's very obvious statement in a way, but anyhow, it's an assumption, but it's a very weak one, I believe. But given that you have this collection, because physics exists, if you couldn't start from there, it would be tough. But in any case, that any system there is a collection of mechanisms or causal mechanisms, and this induces a PCH. Now, just elaborating a little bit more on the PCH, first layer of the PCH is related to observing or seeing. Symbolically, where is my mouse here? Oh, he's here. Okay, hello, mouse. There is the symbolically, we have this P of y given x. We have been trying to evaluate expressions like that for a few hundred years. If you go back to history, beautiful book by Stiglitz. I said 2 out of 2, but maybe this is a good one as well. The story of statistics. But we have been evaluating expression for a long time. What we're doing in the computer science department and succeeded in a big way and have some kind of phase transition in the last 5 years. But there's a process in reality that this X here could be a sequence and can be a 1 billion dimension, 100 million dimension variable. And then you can predict the next one, next token, next word line. But this is the primitive that unleash many of the things that you have here today. In machine learning, we have the supervised, unsupervised, and semi-supervised Circun way. Depending on the decade that you live, there's a different formalism that will allow you to evaluate an expression like that. At some point, we have a base net, probabilistic support vector machine, decision tree, deep neural network. And now is the transformers, that is the language or the type of model that allows us to evaluate expressions like that. Nice. Very hard, by the way, very hard. Not to dismiss, this is why we spend tons of time just to scale up inferences over this guy, trying to give you perspective here, where we are in my point of view. But then you have a different type of language that is related to interventions, the models, P of y given to x, we observe a context C, and we are trying to understand what's the effect of our intervention x in outcome variable y, maybe the survival of the patient 1 year after taking the drug, or whether the person will be clicking or not clicking in the link. If you're Google, you're running these tests, A/B tests, and you are kind of sampling from this distribution. It's very related to the doing. What if I do X? What if I take the aspirin? Will my headache be cured? Again, there is a counterpart from that in machine learning, that is the reinforcement learning, which Sutton and Bartol just got the tooling there for the theory that allows us to do evaluations of expressions like that. Depending, again, of orientation or in time that you live, you have a different formalism that allow us to do inference on top of these distributions, such as a causal base net, a Markov decision process, MDPs, partial observables, and POMDPs, and so on. Now there's a third one that is related to counterfactuals, the third type of capability that I mentioned, or experience that I mentioned. Let me just parse an expression here that is slightly more exotic. After the conditioning bar, we have something that is happening in the factual world. In this world, maybe Joe took the drug that is X prime, and now he's dead, that is Y prime. This happened in this world. Now you can ask counterfactually against the reality, would Joe be alive, that is the Y, that is the opposite of Y prime, had he not taken the drug, that's a subjunctive type of form in the verb, had he not taking, not here is the X, that is the opposite, not taking the drug. Now, there's no experiment in the world even, there's no data. There is a probability distribution that's well defined. And you use that all the time, by the way. It's part of our imagination process. You do introspection, retrospection, credit assignment, blame, responsibility, all these notions that are very important for humans. And the Y type of questions, you can elaborate, they are related to expressions like that. There's no question that in the human cognition, this is a primitive. But in the physical world, we cannot sample from this distribution. Unless we can do time travel, which you don't believe it's no joke. which you don't believe that is possible at the moment. Seems very hard, at least. Because you to assume that you can go back in time, submit Joe to this other condition, and see how the reality will unfold.
By the way, is it kind of similar to chain of thoughts in some way? Because in chain of thoughts, you're like thinking about it, and if I do this, this will happen. If I do this, it seems kind of related.
No, not really in a way that any kind of reasoning that we have any steps. Yeah, we are doing this kind of what if. Here is a very peculiar that is like against it's very broad the connection potentially. By any kind of reason, you can have chains that are long, very peculiar about this type of things that you can formalize a language where there's a form of logic that you have about that, and then in reality, depending on your, I guess, affiliation and flavor, what you like. But there is some kind of the good counterfactuals are the interesting ones, are the ones that there is a clear conflict between our world and this hypothetical that we are. Then, depending on what you do, there's even zero mass. Of course, you don't want to give zero mass, but if you're naive, there's zero mass in this joint counterfactual event. It's more tricky, but I digress. Happy to talk more offline and elaborate. But there's no counterpart exactly in ML about how to do this type of things in a formal and full-blown way. I'm not doing paper review here. I got questions, usually people trying to make me review papers in the talk. I will not do it now. Happy to do it offline. We're not so happy, I guess, but we can do it. But a structural causal model is needed in order to give semantics to questions like that and allows us to start conceiving about what are inferences about this type of object. This is the layer. Observation here is about formalization of the PCH provide a way to measure the capabilities or the expressiveness of different formalisms with respect to increasingly complex queries. Important here, the end, give me a hint, because as you go up, this is the higher level of the hierarchy. If there's the Chomsky hierarchy, right, the same kind of analogous here. Chomsky is computation. Perl is for understanding. You can give all computation in the world, then it will be orthogonal to the discussion that we're having. But now, if you are up in the hierarchy, this is a much more fine-grained type of understanding of the world than the associated, the lower level. Then counterfactuals are more refined than interventions that are more refined than associations. And we kind of proved this result with Icard Thomas, a professor in Stanford, a collaborator and our students a few years ago, that the hierarchy in reality, these layers, they separate in a kind of measure theoretic sense. It's a very nice result. It's called the CHT, the causal hierarchy theorem. But I digress. Now, but why I'm talking that, or based on what I'm talking, I'm here to develop more general and out with the following capabilities, trying to counter the challenges that I mentioned in the previous slide. The first one, I will elaborate and give you examples over time. They are capable of doing causal and counterfactual generation. They are able to have some level of gather causal understanding and be able to articulate causal explanations. They are more efficient and precise in terms of the decision making. They are more kind of surgical. No kind of fat hand intervention, as I say, that you do an intervention, you do a big splash. You can kind of knit. They are more generalizable and robust. And they're able to learn about the world and discover new things. Like a baby, I can kind of evolve the causal model through time. Each part here is a way of saying this related to my book. Each here is a different capability, as I'm saying, and it's a different part of the book. There's a few hundred pages written about each one of them. I'll just give you a few examples here. Happy to discuss other capability if I don't have time. And I spend the whole year in class doing that. Causal inference 1 in the fall, causal inference 2 in the spring, doing this, going over the book. Let me give an example about counterfactual generation, given that it's very general what I said so far. Maybe you would like to take this make me believe type of game, a question about what would a person look like had they been ... This is from kind of venues that publish, like ACML, is this happening soon in Korea, new RIPS. What will happen if they are kind of older? You put 10, you get the picture of the lady, and you ask, how would you look like had they been 10 years older? General purpose, it's not specific about age AI. And this is what we got. This is a couple of years ago, but this is what we got from the Gen AI. And the guy seems completely unrelated counterfactual. This is not a valid counterfactual theorem. Another lady, and you can ask, what would happen had she been from another gender? What is the male counterpart, for example, in the lady, and you get the guy, which hard to say that is the male counterpart. This looks like a different people. There's some kind of mismatch in the age. Let me skip the gray hair here just for the sake of time. Then there's something weird here. This doesn't seem consistent in a way. In the first example, gender is not preserved. And in the second one, age is not preserved. That we would expect. Now, what's really happening, by the way, is related to have this huge latent space, and there is a strong correlation in the data set. This is the Celeb data set, and there is a strong correlation between gender and age. We know that gender doesn't cause age doesn't cause gender. But if you go to the real data, there's a correlation. Males are older and females are younger in this data set. And now this is kind of entangled in the latent space. Then we will go there and say, I want to change age. Given the entanglement, given this correlation, we ended up changing the order. The same with the other features there. Then here is the causal knowledge that the gender and age are correlated in this population. There's another one that age affects the gray hair. It's a probabilistic monotonic relation that whatever age grows, there's a higher probability of the hair being gray. But now, if you use this knowledge that's very parsimonious, very general, that every human knows in a way, and you use that during training, maybe you show the face of the guy and you ask what would happen had it been older, and you get, this seems plausible. This seems a counterfactual pair. It could be, this is the air generator, but it could be the older version of the fellow. Or if you get the lady and you ask what would be had it been a male, and you get this guy, I don't know if it's true, but they even look like having twin brothers. It's plausible counterfactual pair. Then we expect that from the counterfactual generation. And this came in the context of there's a whole discussion in the computer vision. I'm not a computer vision person, but computer vision literature at the time. You have friends and they are sharing that, and you're motivated and affected, causally affected by the discussion. That they are inputting something like that, and they ask, what would happen? They don't articulate as a counterfactual, but they're asking a counterfactual. What would happen if had they been flight attendants? This is the farmers from the 1700s, and then the AI ended up changing the gender. Because there's a strong correlation between job type and gender. And there is huge commotion, zero surprise for the causal analysts because of the correlation. It's like, what do we expect the AI to do? Of course, it's not right, but and this was about what would happen had they been doctors who end up changing the gender of the other. Again, the correlation is in the other direction. But now, why is challenging here? A technical observation is about the sampling from the joint counterfactual distribution, assuming that you have the image. This is the natural distribution of images, and this is the image, the subscript. You already know the semantics, the subjunctive. Why I had x being little x. Had age being this other age, and there's a conflict between those. It's very hard to sample. In reality, it's not identifiable in general. Now, the main result of this line of work is about how can you develop what we call the counterfactually consistent estimators that are guaranteed to preserve some closeness of the worlds, such as the ones that we're saying in the bottom. I'd like to just show a few more examples, given the time, but more recent ones. It's still not published, but I like them. And I think they are even more realistic. Same problem, you get the lamp, abajur, and then you ask, what would happen if the switch on the desk lamp were turned on? And this is what we got from the GPT. This is maybe a month ago. The button is on, but this is not a plausible, this is not a counterfactual pair for this. This is the best AI was doing something like that. It's totally nuts in a way. Not surprising that there is a strong correlation between that in the text, that lamp were turned on, and we have the light coming out of the lamp. This is how the AI is picking the signal, picking up the signal. This is the nano banana, same kind of thing. This is another one. draw what would happen if the cat pushed the vase off the table. That there is a strong correlation between push the vase off the table and something being broken. Now look what, very cute this one, what the AI generated. You wanted the broken to be appearing there, then it decided to remove the cushion to generate something that could be plausible in some sense. Of course, we didn't ask for that. It is not a valid counterfactual pair. It's not a closed world. There's many other interventions, or miracles even called in the literature, between these two different worlds. Something like that in the nano-banana, some kind of off as well in a way. My last one in the image setting, the Coke, and then we ask, what would happen if the Coke bottle were knocked over? And there is some kind of a carpet here. Then you already can see the picture. There's a strong correlation between being knocked over and having some kind of spillover. It's almost an invitation when you have a beautiful carpet. And this is what we got. I think I raised my case, or my case. This is like another banana there also.
It's consistent over multiple attempts, like every time.
Oh yeah, but in multiple images, we have hundreds of those, by the way. I'm just picking some of them, and it's considered cross modality. Modalities. Now we have text that we can do that. Text is just harder to articulate in a talk, but I can give you 2 sentences, and the third one will be off as well. Like in the logical counterpart of model spawning, with the basic logic. A implies B. If I have A, I would expect B. We can have the same kind of similar problem. I will not get B in the case of the. Not surprising in some sense, but it is in the sense that we are in love with the systems, right? And then people are very shocked by this because there's crazy expectations. It's all about the expectations, huh? What's really happening here, by the way, I would like just to use to mention what I have in terms of the before the structural causal model, the collection of mechanisms, and the PCH, and try to connect with what just happened in the pictures. And I call this the challenge of causal generative models, that we have some kind of reality. There is an underlying collection of mechanisms I call M star there that we don't observe. And then this M star induces the PCH, that is these different probability distributions. The observational distribution, that is layer 1 or level 1, excuse me, the interventional one, L2, and the counterfactual one, L3. Many. Observation is just one, but then you have many interventions for each possible intervention, exponential number, and you have even a blowing up of the number of counterfactuals, because those are all versions of reality about how it could be. And this is the real world. This is true nature. But now we have a challenge that you don't observe all interventions and you don't observe all the counterfactuals. You just observe what we observe. And then we're trying to train a model, no matter how complex, can be a transformers, Schwanners, whatever is the name, M hat, no matter how complex. And training here means, and the model has the potential. It has the potential of generating these different types of behaviors or experiences. But now the training here means that we spend, I don't know, maybe a month in the cluster, a few dozen $1 million, and then a little bit of dance and tears and blood. And eventually, we are able to make the model to generate whatever you observe on the other side. This means success in training. Now the question is about, but what about the things that we don't observe? What about the yellow, the interventional distributions? Which kind of statement can you do about that? Then I call this the fundamental problem of Gen AI, that is under what conditions inference in the right side, in the M hat, are valid. In other words, when do they recover the distributions induced by the guys on the left? That is the true M star. Of course, problem just got more complicated if you're trying to do a higher level of the hierarchy, because it's more detailed, as I said. And the problem is exactly the same if you partially observe, because you can have systems that are also agents, quote unquote, right? But anyhow, systems that are doing interventions in the world. Then we have partial observability over the yellow layer. Same problem here about the parts that you don't observe. Everything that you observe, by the way, a side note here. Oh, let me not do side note. Let me not side. Let me do it then. Everything that you just, because it's weird not to do it, but if you observe red, all results are protected in a way by central limit theorem, lower large numbers, or whatever results we like from the ML theory or statistical theory. The interesting setting, and I define causal inference in this way, is about the inference is about when you don't have the right distribution, you collected the data from the wrong distribution, quote unquote. Then how can you do this cross distribution type of inference? It's a new beast here, or new type of inference in the zoo. And it's a possible definition of causality, as I do in the book sometimes. Now that's good. This is generative model. Let me give an example now, for the sake of time, I guess, about understanding and explanations. This is an example in the census data that we have, and this is about how to do data analysis in some kind of more complex systems that are multiple interacting factors. This is real data, by the way. This is chapter 6 in my book, CAI, Causal AI. We have the data science team that observes that there is some kind of disparity between the expected value of Y, that is the salary, between males and females. This is in the data. And the point is like this disparity could be explained in different ways. Different things in the real world may be leading to this type of disparity. One possible one is about maybe there is just the HR or the boss is directly looking into gender and deciding to change the probabilities of or the numbers about what are the salaries based on the gender. And there's a direct discrimination in this case. This is one possible mechanism that seems bad, not kosher, I guess. The other one is about maybe gender is affecting the education level. Right? There's a link here. Gender affects education. Maybe the ladies they are less likely in computer science, less likely to do a PhD. And unfortunately, this is a society issue. But then the company is using you have a PhD or don't have a PhD, and I will give 100K more if you have this label or you have the knowledge of the PhD. Then this link here is the company's business, but this one is society business. But this could be a mechanism because it's kind of being skewed, it's being pulled in the direction. And the other one is like gender is correlated maybe with age or nationality. This is spurious. Age is not causing gender, and gender is not causing age, but there is a correlation there in this data in particular. But then age and nationality is causing the salary. Maybe if you're not a local or don't have a green card, maybe the company is putting your salary down because you're not dependent on them. You want to stay in the country. Now, after some kind of legal argument, the jury may be okay, it may be kosher that Y variations, the variations of this variable Y, due to education. Company will say, I need to be able to use whether the person has or doesn't have a PhD in order to decide salaries. Then these variations are okay, green. But not okay if the variations are due to gender and age. You cannot use gender and age to make your decision. Then the green one is okay. These mechanisms are okay. The red ones are not okay. Now the question is like, but how do you disentangle that? Because in the TV, the total variation, this difference here, which I think is 14K, it doesn't say who generated the variation in the first place. Everything is kind of mixed there, is entangled. No. And the question is how to disentangle it, how to do attribution. I've been here in Israel for some time, then given that there is a lot of discussions on cyber, I decided to have this example, translate the example to cyber, just to show that the example is not only about the census. The census is what we run, but cyber here you can have a user, an employee that is clicking in some type of phishing link, so something related to security, as I understand. And then we have the Y variable that whether there is breach or not breach. Now the variable W is whether someone who stole the credentials of the person, and the confounder is that maybe there is a manipulation campaign, some kind of larger campaign that is generating the variations and is correlated with the click. Other things going on is correlated with the click and that may lead to breaches. There's a causal model that seems good, and you are in the checkpoint building that is good too. The security team sees some kind of disparity there or some kind of gap between the number of breaches given the click and non-click. And the question, what explains the situation? Maybe the click is the one that is directly generating the breach. Maybe it's not the click is leading to the stolen credentials, and the stolen credentials is the one that is leading to the breach. Or maybe there is this correlation there that is spurious. This is not about what we're saying. It's other reasons or other causes. And I just wanted to share. I was proud of the example. And of course, the difference of diagnosing that and say what is really happening, that your budget go in different places of the company. There are different ways of preventing each of these type of incidents. Now, quick one here, the same disentangle. Going back to the example that we run, the data analysis, the previous one is just, I made up that, use my layer 3 counterfactuals, imagination. In reality, running the data, the variation was a 14K, and this is what this is the 14K, and you're trying to say is direct, indirect, or spurious in a way. And depending on the situation, we can have a completely different type of explanation. And again, without the causality, we don't know which one is true. We don't know if we can sue or cannot sue the company. Our level of understanding is relatively low. Nothing in the TV itself tells that this is the right explanation or the other one is the right explanation. Now, I have more, 10 minutes? Yeah, okay. Let me see what I do. 10, right? Or 5? 10, yeah. I'll do a quick one about the robustness and generalizability. This is a setting that you have a color M. It's the basic example that I could think about, that when you have the digit and the color of the digit and the digit itself, and then you create some correlation, as is shown here, between these two things. And then you take a picture, and I have the picture with the digit in the image, and then you have a predictor to predict which digit we have. Classic kind of. Now, yeah, this is already said. We're doing the prediction and so on. And the question is like, why the classifier is answering that this is this digit. Now, we have two classifiers here. One classifier will be standard, or just train and ask the ML students to do, and the other is robust. Robust here is very simple too, that you just remove the color. In other words, we're kind of removing the correlation because now it's grayscale. And this is number one. Number two, we have two distributions here. You have the training distribution, and you have a shifted distribution. Now, for the training one, given that it's a very easy problem, we solved that maybe 10 years or 20 years ago, both classifiers do pretty well. But now we have the shifted one, however we did the shift, and it turns out that the robust one that we remove the color does well, but the standard one does pretty badly. Now, of course, this is constructed by us. Then we know what's going on, because you created this correlation between digit and number, and when you shifted, the thing kind of broke. Now the question is like, do we have any way of diagnosing that? If you open up the classifier, do I have a way of inspecting the classifier and know which one is which? Which one is the standard? Which one is the robust? And here's the method that we have in the literature that's super popular. The most popular, I think, in the world, maybe, that's called SHAP. That is a layer one, anyhow, there's SHAP values. And it's a layer one, is Lundberg, and it's a layer one part. Whole literature and mechanistic interpretability that is huge, in reality can be taught that coming from here or from the line. That's a private version of that, but I would say this is a very prominent one. Maybe just easier, or even worse. But now, if you're trying to do the attribution here, here's the color. You have the digit in the color, and you ask each of the classifiers why you are saying that the number is a 5. Here you're saying, I'm saying that it's a 5 because it is a 5, because of the digit. And I say it's not because of the color. Why is it a 5? Because of the digit, not because of the color, across the two classifiers. Of course, there is something off here, because the classifiers are behaving completely differently. And the point here is like, based on the SHAP, that is a layer one quantity, as correlational, we are unable to distinguish these two classifiers. They seem equally good. We already know that they are not equally good. If you use the counterfactual version of that, it's a layer 3. We call the counterfactual SHAP tree. Now the standard one, we ask, why are you saying that it's a 5? And I say, I'm saying because it is a 5 because I'm doing attribution. Because of the color. It's not because of the digit itself. Then you have an explanation here about why things are happening this way. I think it's very compelling. While the robust is saying that it's a 5 because of the digit. This is why it's robust and it's an easy test. And I was able to get the right features in a way. And anyhow, this is an example of robustness. Most of the mechanistic interpretability is huge in reality. most of the mechanistic interpretability methods used in the literature today are completely oblivious to this layer 2, layer 3. You guys know more than the whole literature in mechanistic interpretability, which is very good and should feel like very empowering and good. Just one more example related to that is very recent, and we're excited. This is from last month, I think. We are running that. We're trying to do root cause analysis. It's called the counterfactual debugging of world models. Let me remember here. You have we train the world model, and you get a very good return in a simulator. And then you go to the real world, and the real world here, there is a little difference between the real world and the simulator. And the difference is about you black out. You create some of the frames, you remove them at random. And then you train, the performance drops very significant. You are playing the Pong game, I forgot to say. And the question, like, do you have a tool to diagnose why the performance drops so significantly? And we do. Using the layer 3 sharply, this is kind of the plot, we are able to pinpoint that this is the frame, this step, and this step are the one that cause the drop in performance. While if you use other methods in the literature, it's all over the place. It's saying, oh, this is the cause, this is the cause, this is the cause. So it's kind of very cheap shot. All over the place, we cannot even handle it, given the massive amount. Then it's kind of off. This is just, I don't need time to interpret, but this is exactly where we're kind of blacking out, and we are kind of running these different methods. There are a few others, including the shot here. And in order to try to pick the signal, to move fast is exactly the same there, just with others. But eventually, you get the frame that is the one that is the true cause. If you go slowly, the reason, this is the 536. The reason, I don't know, 1 second. This is the culprit here, this 536. And the reason is like when you get the 536, the ball is relatively close to the path. Then we need some kind of fine tuning of the path. Then when we black out in this critical moment, the whole thing breaks down. In any case, this is the robustness. Now, I would like to, just to conclude, the question is about taking a step back. I would like to say, where are we? And I think what ties it together, everything that I said so far. And I think the main observation here that fitting the data is very different than understanding what's going on, understanding the underlying mechanisms. These models fit the data extremely well and understand things very poorly. And fitting is about the correlations, understanding is about the causation. And we would like to move towards having better understanding of the models. I like this picture here. It's a new one that I have been articulating, and I'm very proud to plot that is like, I think it's a little summary of the world in a way, that we have this axis here that we're trying to optimize that is related to linguistic fluidity. We are doing pattern learning that is buying us a lot of fluidity in terms of language or visually compelling. The images and the videos that we're generating are kind of amazing, mind-blowing. Then this is where kind of the LLM world is. And this is the direction that we are moving. OpenAI's, Anthropics, and so on, and Google's of the world, natural moving is trying to optimize more of that. Now, causal people, such as me and Pearl, we are there in this y-axis trying to get more understanding. Very mathematical in reality, almost oblivious to the language, to the natural language. And if you continue our natural movement, we are going this direction. This is more effort here, a few more years, and some more money here is like more billions of dollars. This is just a few million, I guess. But the point is like, if you're trying to build AI, or kind of the future of AI, the causal AI, I think we should go here. And we should try to kind of combine these things. Then the question is about non-trivial. I got the question about why you just don't put these two things together. Don't put things together because this is whatever. Those are two different languages in reality that you use to express. This is for the PhD students in the room. I think it's very exciting, analogous to the unification that we're trying in physics to do for 100 years now about quantum and general relativity. It's non-trivial to put this thing together. It's something that they do not match. In a way, I would say that you face similar challenge in the field of AI that people are not even aware. Then you should be aware, and this is our agenda. Now, rather go if you can crack that, our goal is to develop more general and trustworthy AI systems endowed with these different capabilities that I mentioned. I will not read, I can read it again, but do counterfactual generation, have some kind of more understanding, be more precise in terms of the decision making and efficient, generalizable and robust, and to be able to learn about the world. Again, this is all in the book, at least our current state. There are many, many challenges, and I'm just a speaker here. It's a huge effort. Thank you to the funders, and also NSF, Air Force, Navy, and so on, and the American taxpayers. The left is my group, and this is kind of outside collaborators in the right. Thank you very much, and happy to take questions.